Okay, so we are back into the subject here. How do I do this? Okay, maybe like that. We were discussing entanglement, that entanglement is always between two parties, A and B. And now we want to learn a little bit more about this. Wait, I think I need to share it differently because it's somehow jumping. Okay, maybe like this it's clearer. We defined here a Bell state. Here we have a Bell state, and we were studying a bit about. Okay, we were studying a bit about tensor products. Yes. Some examples from last week, some tricks with locality and so on. So some things factorize, some things don't factorize. This is the kind of exercises you can try on a piece of paper. And then we were showing that E(A) tensor identity is like E to power A tensor the identity outside. Those are in principle two different things, but we proved this equality. And then, for example, I was discussing here that if we apply this to a product state, then we have this, yeah? This kind of stuff we were doing. This, for example, on the left-hand side would be an entangling operation in general. We used here, for example, the BCH formula because we showed that those things commute. I was in France, so I said, voila, we were finished with that more or less. So basically, interactions of this type we would call local interaction because there's an interaction term acting either on A and not on B, because here trivially acting, or trivially acting on A and then possibly non-trivially on B. So that would be a local interaction. And we were kind of discussing this a little bit and so on. And we wanted to say that there exists no A and B so that we can turn the entangled state psi, which was defined to be the Bell pair here, this one, so that we get a pure product state, okay? And I was explaining that if you use a non-local interaction, so an interaction of this form, that one example of this is the C0 gate. Such a C0 can disentangle psi, because normally we would take a product state, take a Hadamard on one of them, C0, and then get our Bell state out. But if we do it backwards, we will disentangle the Bell state into a bunch of zeros, okay? And that would be a unitary that in particular has this term, which would be actually Z tensor Z. Okay. Yeah, so local interactions don't change entanglement. And if you think about it, it's a problem like this. Let's maybe explain what the problem is. In particular, we want to use unitaries. So we will consider something like this. And this we will call a local unitary. And A would be Hermitian. B would be also Hermitian. Then we know that U local, the inverse of this is just the Hermitian conjugate. Okay, that's the definition of a unitary matrix. Before I was writing just e to power A and so on, but you can put in some I somewhere. So this is not a big problem. This tensor product locality is more important. But now we want to say, okay, maybe some physical operations. Okay, and what's the space for this? If A and B are 2x2 matrices, so maybe I will write it like this, 2x2 matrices, then we need to find a bunch of numbers, like 4 complex numbers. They are related to each other in some way, but let's say four complex numbers, so maybe up to 8 parameters. and checking all possible values, then check all possible values. And then find that U local psi is never phi tensor phi prime. Okay, one example for this, we had basically this Hadamard tensor identity times C naught on psi was 0, 0, for example. Yeah, so that would be phi here, phi prime, and basically phi is in the Hilbert space of the system A. This one is in the Hilbert space of system B, and here this 0 is a qubit state. This other 0 is also a qubit state. Yeah, just for clarity, this kind of notation. So check by hand. I will just write no. Right? You cannot check all of this. So it's actually a mathematical theorem that we want to prove, that there exists no unitary that is local. This is the definition of a local unitary, such that we can disentangle the Bell state. Okay, so today we will build a little bit of theory for understanding how to prove such a theorem. And we will see that there's something called Schmidt spectrum. So that's the tutorial today. And Schmidt spectrum is invariant under local unitaries. Local unitaries, this U log is an example. Okay, so we need to learn what is the Schmidt spectrum, and the Schmidt spectrum we will get by doing the Schmidt decomposition. So psi A, psi B. This is the most general state of psi and psi B. So what is the state? This is in HA tensor HB. And then again, it doesn't mean that psi AB in general will not be of the form psi A tensor psi B, which would be a product state, we would call it. But this linear space here is the span of a span over complex numbers of psi A tensor psi B, where psi A is in the Hilbert space A. Let me erase. And psi B is where? In Hilbert space B. Okay, which means, so this means that psi AB is of the form K1 until dimension of A, K prime, or wait, I will do J and K. Or even better, I will do A from 1 and B from 1 until dimension B. And here I will have a set of numbers, psi and B. And here I will have some state A and some state B. So basically 0 until dA is orthonormal basis for Hilbert space A. for example. Yeah. So I'm just writing out the most general state that I can get on the tensor product. And you see that this span, this complex span, means that those psi ABs are in C. Okay, psi AB is in C. Okay. So now the question is, how many psi AB? So A goes from 1 until dA, B goes from 1 until dB. So we have a matrix dA by dB. Okay, so we would like to view psi as a matrix which is dA by dB. This is important. Okay, so what does it mean? We had a vector, but you see this is kind of an abstract vector, so we can do different things. And in some way, once I choose this orthonormal basis A and B here, then this ket A and B doesn't play such a big role. And the state is mostly defined through those numbers psi and psi B. And you could write them as a row, but it's maybe interesting to write it as a matrix because you have two coefficients. Okay, and then the next step will be that we will actually work with that matrix, and we will use SVD. So there will exist unitary matrices A. I don't know why I want to write B again. U and V, such that U psi V dagger will be of the form sigma 0, and this sigma is diagonal and encodes the singular values. Okay, so we had this in the tutorials before. There exist unitary matrices. This one will be a unitary matrix on the indices A, and this one will be a unitary matrix on indices B. And once we have this, we almost have the Schmidt decomposition, but I want to show you something else too. So once, basically that will be helpful in a moment, but I was just discussing what is this psi A B indexing here. And let's say I have this. Okay. So now let us do the following. Let me say that A is a linear combination of A prime going from 1 until dA. I will have some set of numbers indexed by A and A prime. And here I will have a set of new vectors. I will call them A with A prime. Okay, so this means this is a different vector than this. Okay, and if I write something like this, it means that basically I can write A as a unitary transformation on some other vector. How would I write it? Basically, I want to have some A prime. Yeah, does it make sense? No. Here I will have a new vector. Let's call this vector A bar. And then this A bar would have a decomposition. It is unitary. So basically, I want to write down a unitary matrix that is rotating a state vector. Okay. So let's say I have A prime, which is unitary on A, I need to figure out in which direction I want to have this. And then, okay, here's the mistake. I can again decompose this in a basis. So this is basis vector. So let's say I have 0, and I want to write 0 as a unitary matrix applied to psi a 0 plus, or in this case, it will be psi 0, psi 1 on 1, which is a unitary matrix acting on a state psi. And this I can write as unitary matrix acting on a psi a. Okay, this should be clear. Hopefully, I'm going to check the chat. Okay. Yeah. So we have those transformations. So basically, if I have a unitary matrix acting on a new vector, I can try to rotate, for example, onto the basis vector. So let's say I have this vector, I have here 0, here is my psi. I can try to find a unitary that brings me here. I can have some phi. I can try to find another unitary that brings me here, and so on, right? Those kind of basis rotations. What I want to show is that if I have this new vector ua prime, then I can write A as U acting on A, right? So just after the unitary rotation here. And then the question is, what will happen with the transformation? So psi AB, A and B. This is just a decomposition of a bipartite state in the basis. But now I want to use a different basis here. So I will write here AB.
So is the prime the same as the bar? Or?
So if prime is outside, then the vector is different. Okay. So in this case it would be the same as the bar, but yeah. Okay, thanks. So there should be a prime. So here I would need to take U dagger and prime here. So prime outside of the cat means that I applied some unitary transformation, and that unitary transformation is maybe defined. So here I would also have this bar. It would be maybe defined by this equation. And here I was just explaining that you know, even if you rotate, you can always decompose what you rotated in terms of the basis. So now A, we will define that A is unitary transformation on some other basis A prime, right?
And dagger.
In this notation, yes. Okay, I will have to have the dagger now, but okay, that will be fine. So instead of A, I need to write this UA dagger, but this will just mean that I sum over A prime, and I have here U star A, I think prime A, and again the basis, right? Is this correct? This, and I will have the some alpha coefficient alpha A prime, because my A prime is defined by this. So A prime, and this can be this index. So it will be alpha A sum over A and then decompose this in the basis, right? So I still put it here, and then I'm kind of rotating it there with the matrix elements. Okay, so let's see. This is simpler than I'm making it, but okay. So this A will be a unitary matrix AB. No, not AB, A prime. I need to put the star somewhere, but anyway, I want to explain the simplest thing ever. That basically here we have some A prime, and in the end there will be A prime on those vectors A prime. Okay, because we are decomposing in that new basis like this. I will just correct whatever is an issue in a moment, but we want to be summing over A prime here and over B, and what we want to define is A prime, A prime here, U A psi A comma B. And if I didn't mess it up completely, then we would see that this is the summation over a transformed matrix UA, possibly dagger here or not, but it just depends on our conventions. And here we have the matrix elements A prime B with some new basis. That it's a new basis means there's a prime outside of the cat, and here I had a prime for just labeling which entry of the new basis I have, B. Okay, the point is that if we change the basis, so let's say we have a basis vector A, and A goes from 1 until D, then we can also define A prime, or we can label it by the same numbers A, which would be a unitary matrix prime outside on A. Okay, so let's say I have this basis and I have like a tilted basis. This is A prime, and it just means this is 0 prime, which means I'm rotating by pi over 4 here. This one I'm rotating by pi over 4. So there's a single unitary matrix that rotates my canonical basis here into the prime basis, which is just like tilting the entries. Okay, so that's why I don't need the prime here, because there's a 1-to-1 correspondence. 0 gets to 0 prime, 1 goes to 1 prime, and so on. Okay, that's this kind of transformation, which means A is A prime with U dagger here. Okay, and the only thing is that I need to make it consistently, so I do it somewhere here. Okay, that's kind of the idea. I'm thinking now whether what I wrote makes sense, but what I wanted to explain is that if we play this game and we define this rotated basis for H, A would be A prime U and A, and for HB would be, oh, the prime should be here, B prime U on B. Okay, so the 0 vector defines for me the new 0 prime vector. The 1 vector defines for me a new 1 prime vector, and so on until D. If we do this, there's no V here. It's two different systems, no? The system of A, the system of V, they do different rotations. Then we should be able to write the vector psi as the summation over AB. And here we would like to have psi U dagger, I guess, V. We need to define those daggers appropriately, but I just want to put it in the form of an SVD. AB, then I will have A and B. This is just numbers. And here I have a rotated basis, okay? So Alice locally rotates her basis. So sometimes we call it quantization axis. And Alice can choose this quantization axis arbitrarily. So she chooses it to become A prime, which is, for example, U dagger on A. Okay. Bob uses V. Then the vector of amplitudes becomes psi prime. It has entries A and B, and those entries are U dagger psi V A and B. So now why do we want to have a singular value decomposition? We need SVD if the dimension of HA, which I sometimes write dA, is not the same as the dimension of HB, which is dB. Otherwise, we can just diagonalize, okay? Otherwise, maybe it's a diagonalizable matrix and we don't need this SVD, okay? But now the point is that we can take the matrix psi and find matrices U and V. Usually this would be the notation, and lambda would be diagonal. If I have a matrix like a Hamiltonian, I can diagonalize it unitarily, U dagger, where on both sides U is the same. Here U and V, in general, U is not equals to V, it's two different matrices. This is because psi can be 5 by 500 matrix, okay? It can be a very weird matrix. If the matrix is rectangular, you can try to diagonalize. But if it's not rectangular, for example, Alice has a qubit and Bob has 50 qubits, okay, 51, they can still be entangled because maybe Bob diluted the entanglement. Entanglement of Bob can be diluted. And what it means is nothing more than doing this SVD and checking the Schmidt spectrum. And this Schmidt spectrum will tell us about the entanglement between those two parties. But now we want to study the example dA is dB is equals to 2. Then we will be studying Bell states. Okay. So when we are looking at the Bell state, we have 1/2 0 tensor 0 plus 1 tensor 1. And what we can say is that this is already in Schmidt form. Okay. If I consider the plus state, tensor 2, then I would write it as 1/2 0 tensor 0 plus 0 tensor 1. If you don't know where this is coming from, go back to a previous tutorial and look at the definition of the plus state. But basically, this is just to give an example of this being in the form psi AB for qubits, yeah? A tensor B. And now we see what we did here. We rotated H would be the Hadamard matrix. So we have this example of H applying to 0, we get this plus state. So we kind of label by what is inside of the cat, but we could say that this is our new 0 prime state. In the new basis, this is the new state prime. And here I can say 1 is a minus, usually we would write with a different symbol in here, but we can say I keep the indices so I can work nicely with matrices, but I just rotated the basis, yeah? So basically what we get is that this is just right in basis. This is general. No structure. Yeah, we don't see the structure here. And this is telling us that this is the Schmidt decomposition. Schmidt decomposition. Because we wrote the state psi S plus tensor plus, which means we found this to be 0 prime tensor 0 prime. We found a rotation that basically compresses the state. So you can write that this is compressed and has structured. Right? Look at this. This has a lot of vectors and is nonsensical. We cannot understand what this is. If I tell you this is a tensor product of 2 plus states, we naturally understand it. And now, basically, what we are saying is that you cannot improve this. A Bell state, so a Bell state here, maybe I should start writing phi. A Bell state has this, and you cannot change the Schmidt spectrum here. Okay? So now, maybe I will check, there's some questions. So now the point is that any state psi, which again, AB, psi AB, A tensor B, I can find a rotation which will give me this A prime unitary acting on A. I can find a rotation so that I will just need to be able to label them like this, and I will have some lambda A prime, tensor B, here A prime. Why is this true? Because if I rotate this state by U with the inverse, let's say, and I rotate this one with V, then those V and B transformations, I can place them as a rotation of the amplitudes. And in the final form of the Schmidt decomposition, we see that the new updated amplitudes are the same as doing the singular value decomposition on the matrix psi. And the singular value decomposition psi tells us that this lambda is diagonal, which means that instead of going over 2 different ABs, I can just take the diagonal entries, which are the only non-zero entries, and I can call them lambda A. And this is the Schmidt spectrum. Okay, so basically Alice can change her basis, can change the quantization axis. Bob can change the quantization axis, yeah. And after they do this, okay, after they change the quantization axis, they can decide to change it in such a way that they, in some way, let's say, diagonalize in quotation marks. For rectangular matrices, it would be closer to diagonalization, yeah. they can choose them in such a way that in the end, there will be only a tensor A prime here, okay? Because everything else is 0. You just compress by doing this singular value decomposition. That's literally how you do compression for different objects in numerical analysis, okay? So Schmidt decomposition is in some way compression of the amplitudes. And we saw the biggest example for the plus state, which is a tensor product state. So there's only 2 local states and you tensor product. Okay, I take this state plus plus. If I write it in the basis, I have a superposition of 4 states, which is not compressed. This is compressed. And this is not compressed. Okay. And what I was showing here with all those transformations, and it was a bit messy, this was maybe the best example. Take this basis and rotate to this basis vector. This is a newt. So you kind of tilt the basis vector, and then Alice can tilt. Bob can also rotate. So when they are tilting the basis vector, they can change it so that they will compress the amplitudes, and we will have this Schmidt decomposed form where there's only one single summation over this dimensionality of Alice and Bob. There's the Schmidt spectrum value, and it's A tensor A. So the first non-trivial example is where Alice is in state 0, Bob is in state 0, and then Alice is in 1, Bob is in 1. That happens each time with an amplitude of 1/2, 1 over square root 2, but they are fully correlated. So if Alice is in 0, then Bob cannot be in 1. Okay, that's a special state. If you would allow for that, you would actually be able to compress more, because if you allow them to be in 0 and 1, then you get the plus state. Okay. So that's what this Schmidt decomposition does. And I think I don't want to prolong for too much. Basically, you need to see that if you will express A in terms of a new basis, then you can start compressing here with those values. Okay. So U starts to act on the psi, and basically this is a more pedestrian way of showing those transformations than on Wikipedia. I will show Wikipedia in 1 second, maybe that will be clearer. Okay, but the key thing is if Alice makes a basis transformation, this acts as left multiplication of U with psi, which is the matrix of amplitude. Bob Trafo is right multiplication. So Bob does V, and then we have psi times V. Now they can choose to do U psi V so that this is diagonal. And when they choose this, they get a transformed state, which is Schmidt decomposition. Okay. So now let's say that Alice does a unitary with the generator A. Bob does a unitary with a generator B. They apply it to their state. Okay. And they get a new state psi prime. And the thing is that basically this has a Schmidt spectrum lambda. This has a Schmidt spectrum lambda prime. You do the same decomposition for both, but this is the same. Why is this the same? Because if this was obtained by U and V, then this is obtained by U times e to IA and V times e to IB. Nothing more. Okay, so basically they can just change the transformations so this local transformation, this is a local transformation. Only changes how to obtain the Schmidt decomposition, but you don't change the spectrum. So lambda is equals to lambda prime. Okay, so now we get our statement. Maybe I will have to recap why all this stuff is true. But you see that if we don't change the Schmidt spectrum, here, then basically Bell state has lambda 0 is equals to 1/2, and then lambda 1 is also 1 over the square root. I always say 1/2, but okay. Any product state, let's call it phi, which is phi with some other phi prime, has lambda 0 is equals to 1, and then lambda 1 is equals to 0. Here we will say it has a rank 2, and this is rank 1. So in terms of Schmidt spectrum, product states rank 1, and states rank strictly larger than 1. Okay, and we have our theorem: local operations don't change the rank. Okay, and that shows the impossibility. I was kind of sketching it somewhere there, right? I was saying you have maybe 4 parameters for that unitary, 4 parameters for the other unitary. For every unitary, you need to check that you will never get a product state. And now we use the Schmidt transformation to show that you cannot change the rank. So how could you disentangle a Bell state with those operations? It's not possible because the Bell state has 2 non-trivial Schmidt values, while we would like to transform it into a product state which would have only 1 Schmidt value, which is non-zero. Okay, and that's impossible because we just saw that we don't change the Schmidt spectrum, we only changed how we get to the Schmidt spectrum. Okay, right? So let me just discuss this a little bit more. So basically, if Alice does an operation U, Bob does an operation V, then they get a new state with an amplitude which is U psi V dagger somewhere or something like this. And how this works is that basically we will do U tensor V on psi, and we will have psi A B. Then U will act on A, and V will act on B. Okay, but you see it's the same thing here. No, I mean, this is again over a basis of products, so this becomes psi A B over A prime tensor B prime. And if I want to enter here, if I want to express this new state psi prime in the old basis, then I see that I need to take psi IB and take what is A prime, and A prime is U A prime where the index is inside and we have the old basis, yeah? A prime, A prime inside. And then here I will also have, so this is the summation over A prime. I will have B prime, B, and the prime is here, which means that previously I had a different vector, but this vector I can express in terms of the previous basis entries decomposition, but it will not be B anymore because we are tilting the axis, but it will be a summation. It will be summation over all possible vectors B prime. So now we can exchange the summations. And we go outside with the prime summation. And to go outside with the prime summation, we need to do the AB summation here. Psi AB UA prime, VB B prime. So for this transition, we are using this associativity linearity of the tensor product. And now we have the old basis, but with new indices. B prime. Okay. And we are almost done with all those transformations. Yeah. Because I can write here A prime, B prime. I can write a new psi with matrix elements A prime, B prime, and my old basis, but with other indices like that. And now I can just relabel. I can just write AB psi. I don't need this anymore. Psi prime A B A tensor B. Why is this possible? It's possible because we have a new vector and we found a new set of amplitudes for that new vector in the previous basis. Yeah. So psi prime in this case would be U psi V. And to do this, just do the matrix multiplication and check whether there's a dagger somewhere or not. Okay, I don't do this now. It's the tutorial part. So there might be a dagger somewhere. Okay, but you can relabel things. And then you can find that you can choose this to be, if you choose them to be coming from the SVD, then you get the SD, the Schmidt decomposition, where this is diagonal. If you chose them wisely, you will have compressed the state, and you see nothing happens, no? It's invariant, the Schmidt spectrum. Okay. So now if I transform by this U and V, we see that the Schmidt spectrum will not change because I can use the previous U and V just by the transformations we applied just now, and the Schmidt spectrum will be again popping up. Okay. So under local transformations, there's an equivalence of certain states, and this Schmidt spectrum is compressing stuff. Okay. So I was also saying it somewhere here, maybe. The number of those amplitudes is d by d. Okay, it's a big vector, but suddenly we get a smaller Schmidt vector, which is d, which is the essential information for bipartite correlations. So this has redundant information for bipartite correlations, and this is essential information. For bipartite correlations. Okay, that's the Schmidt value. Yeah, and then a simple thing, the question: how many non-zero Schmidt rank values do you have? That's the Schmidt rank, right? How many non-zero Schmidt values in the Schmidt spectrum do you have? that stays invariant under local transformations. This is all that we were showing here, because if I apply those unitaries U and V locally, this is local, then I cannot change the Schmidt spectrum because I get this new decomposition here, but I can just choose all this stuff and it will stay the same. Okay. So that shows the impossibility of using local correlations. So to disentangle the Bell state. So to disentangle the Bell state, Alice and Bob need to come together and make a non-local operation that way. That's how you physically make non-local operations that create entanglement. We were discussing it somewhere there. Okay. So I think that was roughly the recap, right? Okay. So basically it was all about writing things in a basis. And we saw that if we are changing the local basis, we are changing the vector of amplitudes. And if we write the vector of amplitudes as a matrix, that was this this way of writing this as a matrix somewhere here, I think, right? Then we can make certain transformations of the matrix, and then we do standard compression using singular value decomposition. And the spectrum of the matrix is what matters, and not the basis where the matrix is located. And that spectrum has certain properties. For example, by local operations, unless Alice comes together with Bob, they cannot change the rank, the Schmidt rank of their state. Okay. So if they are given a Bell state, their Schmidt rank is 2, and they cannot change it on their own. They need to come together to change it, which means they cannot disentangle, and that shows something about entanglement, that this is a non-local property. Okay, it's a different type of correlation. Okay, I will finish here, I think. Yeah, for now, that was the discussion. Okay, so a simple thing, just transforming amplitudes, then you transform with the SVD. And you see that you cannot disentangle Bell states, which is the sound way of showing that the entanglement cannot be destroyed locally and it's a local resource and stuff like this. It's a bit abstract mathematically, and there was a little bit of tricks with indices, but let me show it here. If we look at Schmidt decomposition, you can do it much faster without this yata that I was saying. But you need to do some tensor notation, and I don't know if this is more intuitive. Just to say on Wikipedia is much shorter and it's maybe a bit nicer, and you have this description here of all those Schmidt ranks and entanglement on Wikipedia. If you just Google Schmidt decomposition, okay? The Wikipedia page for that is a bit more compact. Maybe gives you some more clarity. I would say if anything that I said is not clear, just try to use my kind of descriptions to make it work with Wikipedia. I'm not sure if this is as intuitive. Maybe it's easier if you use the Schmidt unique